Okay. So we have ionic compounds, we have covalent compounds. We've talked about both. Ionic compounds come together through the opposite attraction of their charges. Okay? Covalent compounds come together because of sharing of electrons. And this creates different properties for these different compounds. So we're going to look at a few of their properties that are associated with things that are ionic or things that are covalent. Okay, so the physical state, ionic compounds are solids at room temperature. Covalent compounds can be solids, liquids, and gases. You can have all kinds, and that is because there's a wide variety of properties within the covalent compound group, okay, due to polarity. And we'll talk about that in a little while. Melting and boiling points. The melting point is the temperature at which a solid is converted to a liquid. Boiling point at which it is converted from a liquid to a gas. So those properties of these will be different within these two groups. Okay. The melting and boiling points of ionic compounds are much higher than covalent compounds, like ridiculously higher. So it requires a large amount of energy to break those ionic bonds, to cause them to separate. Okay? Ionic compounds typically melt at several hundred degrees Celsius. All right? Ionic compounds are usually crystalline solids. They form solids because they're salts. We refer to them as salts. And they form crystalline structures. Covalent compounds can be crystalline or have amorphous structures as well. Okay, so they can have both once they're solids. All right. Ionic compounds can be determined as electrolytes. They are electrolyte, meaning that when the ions are present in solution, it allows them to conduct electricity. Covalent solids, if you put it into solution, if you dissolve it, they won't conduct electricity. Okay? But ionic solutions would conduct electricity. So if I take this salt in my house and I dump it in some water and I pass an electrical current through it, I can light up a light bulb. Okay? So the light bulb would light up. But if I took some sugar and I dissolved it in water and tried to conduct electricity through it, it wouldn't work. I wouldn't be able to light up the light bulb. Sugar is covalent. Sodium chloride salt is ionic. So the sodium chloride breaks apart in the water, becomes sodium plus, Na plus, and Cl minus. Whereas the sugar molecule just stays together as a covalent compound. It doesn't break apart. It doesn't create ions in solution. Okay? So that's a big difference between ionic compounds and covalent compounds. Ionic compounds break apart in water, whereas covalent ones will not. So ionic compounds will conduct electricity. These ones won't. Okay? So what about water then itself? Does water conduct electricity? Is water ionic or covalent? Here's water. H2O. Is it ionic or is it covalent? Is it a metal and a nonmetal, or is it nonmetals? Nonmetals, so it is what type of compound? So does it conduct electricity? No. It is a covalent compound. It does not conduct electricity.
Then why can you get electrocuted in water?
That's the next question. So why can I get electrocuted in water?
Because there's something that's...
Because that water is not pure water, right? What's in? You turn on your bath water, it's not pure water. Sorry to tell you guys. Okay? What's coming out of there? Lots of minerals. All kinds of minerals. So you drop your toaster in your bathtub, you're toast. Okay? Because of all, that's pretty good, right? Because of all the minerals. Because of all the minerals that are in there. It's conducting electricity because of all the ionic minerals that are dissolved into it that can pass electrons and conduct electricity. But if you fill your bathtub up with distilled water from the store, go buy some from the store, it's not going to conduct electricity. You're perfectly fine. Okay? But it's all that, what does our water run through? It runs through the aquifer, which is underground in rock, right? What's rock? Rock's minerals. And all those minerals are dissolving into your water. In fact, let me see your water. Okay? Purified drinking water does not mean it's pure water. This is not pure water. Sometimes it says that they add minerals for taste. This one doesn't say it. But you could look on your bottles and it says minerals added for taste sometimes. That's because if you drink pure water, just distilled water, you probably think it's disgusting. Okay? Because you're used to drinking water that has minerals in it. It's the spring water or whatever, the natural spring. That doesn't mean pure water. That just means it comes from a natural spring, which was underground, which is in rock. It has all the minerals in it that you like and taste good. Okay? And they probably purify it from bacteria and whatever else was in there. So, all right. So ionic compounds, metal, nonmetal. Covalents are two nonmetals. Electrons, they're completely transferred here. They're shared in covalent compounds. So that's the big difference, right? Physical state, they're solids or crystals. Covalents can be any of the states, solid, liquid, or gas. And if they're a solid, they're in the crystal or amorphous state. And we'll talk about that a little more later. But dissociation. Do they dissociate? Ionic compounds, yes, which makes them electrolytes, which allows them to conduct electricity. Covalent compounds are not electrolytes. They will not conduct electricity. They have ionic have high melting and boiling points. Covalent compounds, relatively, if you put it in perspective, are way lower, have much lower, okay? But within the covalent groups, you have a wide range. I'm talking hydrogen. Well, actually, let's just go to this one. Carbon dioxide is a gas at room temperature, right? If you get it cold enough, it will become a solid. Have you guys ever bought dry ice? That's solid carbon dioxide. It's very cold, right? It's way colder than your freezer. You put it in your freezer and everything in your freezer gets super hard because it's way colder than your freezer. It's like negative 120 degrees Celsius or something like that. So, you have to be careful handling it. You can't touch it directly because it'll burn, however you want to say that. It'll burn your finger from freezing it. So that's bad. So carbon dioxide is very cold. It's a gas at room temperature. Water is also covalent. Okay? And at room temperature, it's a liquid. So you can see within the covalent group, there's this gigantic difference. A huge difference between the freezing temperatures and boiling temperatures of things that are covalent. Okay? And the reason for this difference has to do with something called polarity, which we'll get into pretty soon. I think by the end of this chapter, we'll talk about polarity. Okay? And how that affects the boiling and melting points of these covalent compounds. Okay? Okay, the next really fun thing, apart from naming, drawing covalent compound structures. All right? And there is a very specific set of guidelines that if you follow will allow you to draw these successfully. And it's very easy if you learn it correctly. But if you try to be all cavalier and make up your own rules and try to draw it on your own, you're going to do it wrong, okay? Because I tell you to do this very specific set pattern, and then you guys go and you're like, oh, I'm going to skip that step, and oh, I know what's going on. And, okay? Don't do that. Just follow the guidelines. If you do it, you follow them perfectly, it will always come out correctly, and it'll be very easy to draw these structures, okay? All right, so drawing Lewis structures, guideline number 1. We're going to use the chemical symbol, all right, for these compounds, and we're going to write a skeletal structure of the compound. And the guidelines that they're going to go through, I might put them in a more organized fashion or easier to understand fashion after we go through them, okay? Okay, number 2, determine the number of valence electrons. You definitely want to do that. First thing you want to do is determine the number of valence electrons on each atom in the compound. Okay? So if I have carbon dioxide, how many valence electrons does carbon have? 4. How do you know? The periodic table tells me, right? I look at the periodic table, I see carbon, it's in 4A, group 4A, or I count over 1, 2, 3, 4. It's the 4th element in period 2, which means it has 4 valence electrons. Okay? Oxygen. How many valence? 6 times 2, 12, right? Okay? 12 plus 4, 16. Okay? You guys are like, Mr. Crandall, you can do that on your own. Why are you making us do it? I want you guys to think about it. Okay? So, 16 electrons. So this carbon dioxide molecule has 16 valence electrons. And valence electrons are the only electrons that matter in structure because they are the ones that create the bonds and cause the structure to be the way it is. All the other electrons don't matter. So we don't care how many total electrons are on carbon or oxygen. All we care about are how many valence electrons they have, because that's going to determine my structure. So there are 16 valence electrons on a carbon dioxide molecule. So if I draw a carbon dioxide and it has 18 electrons on it, it is wrong. Okay? If it has 20, it's wrong. If it has 14, it's wrong. So it has to have 16 valence electrons to be carbon dioxide. Okay, so connect the central atom to each of the surroundings with single bonds. So carbon connected to oxygen, connected to oxygen. Okay? Complete the octets of all atoms bonded to the central atom. Okay. How many electrons are usually around oxygen? 6. But what this is telling me is that I need to complete the octet. Okay, so do that. Remember what I told you, you have to follow these rules perfectly. Don't just assume, oh, well that's 6, so I'm just going to put 6 here. No, you have to follow the rules. The rule is everything has to have 8 electrons. Everything has to have 8 valence electrons. That is a must. It doesn't have that number. That's how I count how many valence electrons I have overall. But when I draw the structure, it has to have 8. Okay? Okay, so this is my starting point. That's how I start everything. I start it where I put all the atoms around the central element, and then I complete the octets on everything. 2, 4, 6, 8. 2, 4, 6, 8. Remember, these lines represent 2 electrons. Okay, the bond is a sharing of 2 electrons. 2, 4, 6, 8. Everything has 8 electrons. They all have 8. That's how I should start every single compound that I try to draw. Okay? So that is the first step. Now, if it was hydrogen, let me just show you with water. I would only need to complete the octet on oxygen because hydrogens cannot hold 8 electrons. So that is an exception to this kind of rule, complete the octet on all atoms, except for hydrogen. Hydrogen only has 2 electrons. So I draw a single bond on it and that's it. That's all it can make. Hydrogen would never be a central element because it can't make 2 bonds. It can only make a single bond, and so it's always on the outside. Okay? Because it'll be bonded to something else. Okay, so that's what this is saying. Hydrogen needs only 2 electrons. Okay, so these electrons that I've put out here, they are called lone pairs. They are lone pairs. I have 1, 2, 3 lone pairs on that first oxygen. I have 2 lone pairs on the carbon and another 3 lone pairs on the other oxygen. Okay? Okay, next guideline. If there are not enough valence electrons to give the central atom an octet, move lone pair electrons from terminal atoms to form a new bond with the central atom. What the heck does that mean? Okay, let's look at it. So this was our starting point. We have 8 valence electrons on everything. Okay? Now, if I count the number of electrons in this structure, there are 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. There are 20 electrons in this structure. That's too many, right? That's because this is my starting point. I now have to manipulate it to be the right number of electrons. But I have to start here first. Okay? So, what this guideline is saying here is form bonds. If I have too many electrons, what do? I form a bond. So, just kind of do that here. I'm going to make a bond between the carbon and the oxygen. Okay? But when I do that, that is actually just adding electrons, right? So I added 2 more. So to maintain the rule of 8, I will have to remove electrons now. How many electrons are on this oxygen with that double bond? 10. So that's too many, so I have to remove a pair of electrons. How many electrons are on the carbon? 10 also, right? So I have to remove electrons from the carbon as well so that I can maintain the rule of 8. Right? Now how many electrons are on that far oxygen? 8. And on the carbon? 8. So I have 8 on each. That's what I want. Everything is following the rule of 8. It has to. If it's not, you're doing something wrong. It has to follow the rule of 8. Okay? How many electrons do I have in all? Okay, so it went from 20 to 18. Every time I make a bond, it reduces the total number of electrons by 2 because I added 2 electrons and removed 4. So it goes from 20 to 18. That's not enough. I need to get to 16. What am I going to do? Yeah. Okay, make another bond. Remove electrons from both things that I bonded to. How many electrons are on my structure now? 16. 15? Oh, you guys. Okay. So I have how many now? 16. 16 electrons. That's what I want, right? So I look at this and I say, okay, I have 16 electrons on my structure. Is every molecule, is every atom following the rule of 8? Okay, let's count this oxygen. 2, 4, 6, 8. It has 8. This carbon, 2, 4, 6, 8. It has 8. This oxygen, 2, 4, 6, 8. It also has 8. So everybody is following the rule of 8 like they should be. So this is my structure. Okay? That's my carbon dioxide structure, which they're going to show us here. Okay? So here we go. Carbon dioxide. Okay? And we get there. And that's our carbon dioxide structure. Okay? Okay, let's try this one. Carbonate. CO3 2 minus. The only thing that is different about this is that it has a 2 negative charge on it. So what does that mean? If I have a 2 negative charge on something, what does it mean? What's that? Okay, I would have to with another metal if I was going to make a compound, that's right. But what does it, in itself, a 2 negative charge means what about that? It has 2 extra electrons. That's what it means. Okay, so carbon has 4, right, valence electrons. Oxygen has 6, 6 times 3. 18. 18 plus 4. 22. Now, because it has a negative charge, I need to add 2 more electrons. Plus those 2 extra electrons, so my structure should have 24 electrons when I'm done. Okay? So I started out carbon surrounded by 1, 2, 3 oxygens. I make my bonds. I show the lone pairs. Everything has 8 electrons on it. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Everything has 8. How many total electrons are in this structure? Well, this oxygen has 3, right? This one has, 8.
26.
They all have 8, right? That's right, it is. 8 times 3 is 24 plus these 2, 26. So there's 26 electrons on this structure. Okay, that's kind of the easiest way to count those. So 26 electrons, that's where I'm starting. Is that what I want? So what do? Make a bond. Okay? And I can choose any of those 3 oxygens, it doesn't matter. Okay? So I choose one, I make a bond. Now what do I do? Because it's at 28 now, I don't want to be at 28. Is everything following the rule of 8? No? So what do I need to do? I need to take them off of oxygen and carbon both. Okay? Now let me show you what some of you will probably try to do at least once, and then I'll tell you don't ever do that again. Okay? You want to do that. Is that 24 electrons? I had 26. I took away 2 more. I have 24. So what's wrong with that? Say it louder. It's not following the rule of 8. Big mistake, right? 2, 4, 6. That's not right. It has the correct number of electrons, but it is not following the rule of 8. You have to maintain the rule of 8 and have 8 electrons on everything. That's the same thing. And what am I trying to say? And have the correct number of electrons. Okay? So I need to make the bond. Make sure I'm following the rule of 8. So instead of having separate pairs, I share them into one pair. So that reduces the total number by 2. Okay? But it maintains the correct number it maintains the rule of 8 on everything. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So it still has 8 electrons. Okay? So this is the correct structure for carbonate. Okay? Okay, so carbonate's a polyatomic ion, so you can represent the charge on it with brackets and a 2 minus here. Okay? All right, let's practice. So I want you guys to draw these 5. Draw those 5 molecules. What do they look like?
know the octet. 2, 4, 6, 7. Have 8. Okay. So when I made a bond, I removed this from here. Now 2, 4, 6, 8, 10, 12. Let's start over oxygen. Okay, so go ahead and put oxygen in the middle. Bonded to 2 hydrogens. Okay, now hydrogen can only ever have 2 electrons. So I don't put electrons around it. Okay. And then I flip my oxygen doesn't need 8. So go ahead and put the octet on it. Okay. 2, 4, 6, 8. How many do I need? Okay. Okay. So you'll find the same thing happens here. So go ahead and redraw that one. Wait, up. 6. But you need to put 8 on it to start. Okay, so that one that you just wrote is represented by the bond. So you don't have to write it. There you go. 2, 4, 6, 8. Hydrogen has 2. Hydrogen has 2. That's all hydrogen can have. I want 8 total. So 2, 4, 6, 8 is how many I have.
Okay, so let me just go over a few of these now that you guys practice them, because I'm going to clarify a few things that I see as common mistakes, okay? So let's start with water, okay? Water. Oxygen's in the middle, surrounded by 2 hydrogens, okay? I start everything with 8 electrons on it, except for hydrogen, because hydrogen can only have how many electrons total? 2. Okay, so this is my starting structure for water. How many total electrons? Well, oxygen is 6 plus 2 more for hydrogen. That's 8. So I need 8 electrons here. Okay. How many do I have right now? 8. This is my structure. Okay. Ammonia, NH3. Nitrogen has 5, has 5 plus 3 more hydrogens. That's 5 plus 3, 8 electrons. So let's start the structure. Nitrogen bonded to 3 hydrogens. Hydrogens cannot have more than 2, so they are done as they are. But the nitrogen does need 8. So I put a lone pair there, and I get 2, 4, 6, 8. There's 8 electrons in my structure as it is right now. That's my structure. Okay? We already did carbon dioxide earlier. I guess we could do it again. Carbon surrounded by oxygen, surrounded by oxygen. I start everything out with 8 electrons. There's 20 electrons in my structure as it is right now. I need 16. So if I calculate how many electrons you need on carbon dioxide, it's 16. Okay, I have 20 in this structure. I need to get to 16, so I make a bond, and I remove electrons from both of the elements I bonded to. That brings me from 20 to 18. It's not enough, so I need to make another bond and remove electrons from both things. Now I'm at 16. This is my structure. Okay? NH4. How many electrons do you need on NH4? Nitrogen has 5 plus 4 electrons is what? 9. But there's a positive charge, which means I do what?
Take away 1 electron.
Subtract, so I need 8 electrons. Okay? So N, H, 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 H. How many electrons are around nitrogen? 2, 4, 6, 8. How many are around each hydrogen? 2. Everybody's happy. I have 8 electrons in my structure. That's my structure. Okay? Okay, N2. Nitrogen has 5 electrons. 2 of them would have 10 electrons. Okay, so how are they going to bond? I start everything out with 8. If I count the number of electrons in my structure as it is right now, how many are there? 14. There's 14 here. 2, 4, 6, 8, 10, 12, 14. Okay, there's 14 electrons in that structure. I don't want 14, I want close, a little more than 8, 10. Okay, we counted it as 10 electrons. Each nitrogen has 5. 5 times 2 would be 10. So a total of 10. So I need to reduce the number of electrons in my structure, but still maintain the rule of 8. The only way I can do that is by making a bond and removing electrons from both of the things I bonded to. That reduced it from 14 to 12. It's not enough. So what do? Make another bond. This is my structure for nitrogen.
Does it matter where on, like around the end where the electrons are?
No, it doesn't matter. All that matters is you have the correct number of bonds and the correct number of electrons. Okay. All right. So that's how I would draw those. Now, these bonds, okay, when we talk about how strong they are, if you have a single bond versus a double bond versus a triple bond, okay, as you increase the bond number, you're increasing the stability, the strength of the bond. So a triple bond would require more energy to break it than would a single bond. Okay? A single bond would break more easily than a triple bond would. Right? And that has to do a lot with the bond length. So the bond energy, most energy to break it, to single bond, least energy. The bond length, single bond is the longest. Triple bond is the shortest. That makes sense? Because if it's the longer it is, the easier it is to break. The shorter it comes together, it's harder to break. Okay? So that's how these come together. Which brings us to a very interesting concept, because if you think about when you ignite something, you ignite it, it's going to burn in the presence of what in the air? Oxygen, right? It's going to burn with oxygen. Well, that's strange because there's way more nitrogen in our atmosphere than oxygen. Nitrogen is the most abundant gas in our atmosphere, and oxygen is second to that. So why is it burning with the oxygen and not the nitrogen? Well, let's draw the structure of oxygen. And we just drew the structure of nitrogen. So now, can you tell me why? Why is it that when I turn on my Bunsen burner and I ignite it, the propane is going to burn with the oxygen in the air to create a flame rather than the nitrogen in the air? Has to do with this right here. because this is stronger than that. It requires more energy to break that bond than it does to break that bond. So the oxygen will react first because the energy requirement is lower. And so therefore I'll burn it with the oxygen in the air rather than with the nitrogen in the air. Okay? All right, now in your car engine, you'll probably get some nitrogenous products because it's super hot in your engine and you'll have enough energy to break that bond. And so, you have a catalytic converter to scrub out all that noxious chemicals that come out of your exhaust before they kill everybody. Okay? All right. So here it's just going to go through another idea of with this double bond. And so we drew carbonate earlier. Carbonate, double bond, oxygen, oxygen, oxygen. And we had 8 electrons around all these oxygens. Okay? You can't see those valence electrons very well, can you? Okay? And we said you chose one of those oxygens to double bond to. But is that the correct one? And we said it doesn't matter. Why? Because of resonance. This is what we call resonance. You see the double bond, how it's flipping around? So really, if you were going to draw this structure, you would have to draw it with all 3 of these structures to make it the most correct structure. You don't have to do that, but that would really be the most accurate way to draw this. Because that would represent that double bond is moving. And it gets even more strange than that because it's not actually even moving. It's resonating through the entire structure all at the same time. So none of these Lewis structures actually exist. Okay? The actual structure is an average or a hybrid of these 3 structures. So resonance, 2 or more Lewis structures that contribute to the real structure. So you have those structures that are contributing to the real one. Oops. Oh yeah. So experimental evidence shows all bonds are the same length. That's strange because this one should be longer than this one, right? Well, so they've done experiments and found that all 3 bonds are all the exact same length. There's not really any double bond. There's a hybrid bond, and it's resonating through the entire thing. They all have the exact same length of bond. Okay, so that's the idea of resonance. And after that, you don't really have to know much about it. Okay, don't worry about it. But that's what that double bond is doing. It's resonating. Okay. There are some exceptions to the octet rule. We already talked about one of them, hydrogen. Hydrogen can only have a single bond because it can only hold 2 electrons. There are 2 others. Okay? Beryllium is the other one. Beryllium only has 2 valence electrons, so it can only share 2 electrons. It can spread its electrons out and make 2 individual bonds from those electrons and share them with something else, like hydrogen. So if you look at this structure of beryllium, beryllium does not have 8 electrons on it, right? It only has 4. That's all it can do. It can't do anything else than that. Okay? Beryllium will not have 8 electrons on it. It is an exception to the rule of 8. It will, once it's bonded, it will total it'll have 4. Okay? Don't worry about odd electrons. I'm not going to do anything with that. Wait. Okay, it's not going to tell me about the other one? Fine. All right, the other one is boron. Okay, and this is the one I more commonly use, so I expect you guys to know it. Okay, boron. So if I want to draw the structure of BH3, I would say boron has 3 valence electrons. H3, that's 3 more. So that's 6 electrons total. You can't even form an octet from 6 electrons, right? This is an exception to the rule of 8. I cannot have 8 electrons on boron. So when I draw the structure B, H, 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 that's it. There's my 6 electrons. I'm done. I don't have any other electrons. I cannot satisfy the rule of 8 with only 3 electrons on boron. Okay? So it is an exception. But once I get to carbon, carbon has 4 valence electrons. It can make 4 bonds. It can satisfy the octet. Okay? But before that, so before I get to carbon, I cannot. Everything else can. Okay? It's just boron and beryllium. Those are the ones that come before carbon. They're the ones. Okay? Lithium is too much of a metal. It's not going to form any covalent compounds. Beryllium barely does it. Okay? But you can form a BH3 or BEH2 molecule. Okay? Which is fairly covalent. All right? But those are the 2 exceptions, besides hydrogen, that I expect you to know. Okay? And you don't need to know this. Don't worry about that. Expanded octets. We are going to briefly talk about expanded octets, but you are not going to have to really do much with it. Okay? What I want you to focus on is learning how we learned to draw structures just a minute ago. That's what I want you to focus on. With expanded octets, it kind of has a few other rules that you would need to follow, but I don't want you to focus on these. Let me explain it, though. So if I run a reaction between phosphorus and chlorine, I get 2 outcomes. I get PCl3 and I get PCl5. Well, that's weird. So if I draw the structures of these, P, Cl, 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 here's my phosphorus, trichloride. Okay, that one's okay. It's following the rule of 8. I need 26 electrons. It has 26 electrons. Great. Right? Okay. P, Cl, 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 Cl. What is wrong already? How many electrons are on phosphorus right now? How many valence electrons are on phosphorus? I should have 8. How many do I have? 10. So, but these 2 structures are created. I create both of those things. How come? Well, because there's an interesting thing about phosphorus. It's in which principal energy level? Look at the principal energy level. What principal energy level is phosphorus in? 1, 2, 3, 4. Which one? 3rd. It's in the 3rd principal energy level. This is the 3p, right? Well, phosphorus is in the 3rd principal energy level, which means it has 3 sub-energy levels. It has an S, a P, and a D. Right now, phosphorus has no electrons in its D sub-energy level. There are absolutely no electrons in it. So what it decides to do is, so here I have phosphorus, and these are the S electrons, and these are its P electrons. It can make 3 bonds, right? Because it has 3 unpaired electrons. But it has 5 total electrons. So what it can do is, instead of having all of its electrons in S and P, it can spread all 5 of its electrons out because it has a D sub-energy level. And now it has 5 unpaired electrons. And because it has 5 unpaired electrons, it can create 5 bonds. So we call this expanded octet. It has an expanded octet. So the expanded octet allows it to make more bonds. Could nitrogen do that? Why not? Phosphorus can do it, so why can't nitrogen do it? It's in the second energy level. Does it have a D? Nope. Does not have a D. It doesn't have a D, so it cannot do that. So all of these guys, they could never have an expanded octet because they don't have a D sub-energy level to push their electrons into. These guys, they have empty D sub-energy levels. They can push their electrons out there and create 5, 4, 6 bonds. Okay? So basically, anything past this first group, they could do that. These guys could all expand their octets if they wanted to. Okay? So that's what we see up here. Okay? Phosphorus pentafluoride, PF5. So it can expand its octet, and it can do that. Okay? All right, let me just quickly start this, and we won't finish it today, but we will finish it next time. Okay, VSEPR theory, valence shell electron pair repulsion theory, is helping us to understand how the structure of these molecules actually looks. So I drew some structures. So let's say I draw water. Here's water. Okay, it has some valence electrons. Here's water. Which one of those is more correct? Well, in reality, what does water look like? It looks more like this. This is not incorrect. You can draw it that way. But when you describe its shape, you can't describe it as linear because it's not a linear molecule. Water takes the shape, this configuration, this bent shape, because the lone pairs force it to. If you have something that doesn't have lone pairs on the central element, then it is linear. This is a linear molecule. There are no lone pairs here. So these oxygens, they get as far away from each other as possible, which is completely 180 degrees from one another, right? So they're 180 degrees away from one another. They're perfectly linear. But water, because of the lone pairs, when those lone pairs are added to that central element, they force the hydrogens down because they're taking up room. They force those hydrogens down, and now it's taking on a different configuration. It's bending it. So we say it has a bent configuration, okay, because of those lone pairs. So when we talk about valence shell electron pair repulsion theory, we're going to start to describe the actual shape of these molecules. Okay, so we'll do that next time. We'll see you guys next week.
I have a question. On this one right here, how did